This next set of videos covers the Chapter 2 lecture notes. It is broken down into two videos, slides 1 through 18 and slides 19 through 40. In this video, we will discuss the concepts behind acid bases as they are related to organic molecules. There are three different definitions of acids and bases in organic chemistry: Arrhenius acids and bases, Bronsted Lowry acids and bases, and Lewis acids and bases. You hopefully remember these names from general chemistry. Each definition of bases has its purpose in organic chemistry, and we will now discuss each one of them. Arrhenius's definition of an acid and base is that for an acid, that's any molecule which produces an H+ in water. H+ being called a proton or a hydronium ion. And an Arrhenius base is any compound that, when put in water, produces a hydroxide or an OH- molecule in water. So, Arrhenius's definition of acids and bases are only applicable in aqueous solutions. You have to be in water. Bronsted and Lowry independently expanded on that definition, and they said a Bronsted Lowry acid is any molecule that is a proton donor, meaning it gives up an H+, and that a Bronsted Lowry base is any molecule that accepts a proton. Later, Lewis expanded on the Bronsted Lowry definition, and he defined the Lewis acid as any molecule that's an electron acceptor, which means it still could donate a proton, and any Lewis base is any molecule that can be an electron donor. I'm not sure you recognize any of these people, but you might recognize the one in the middle, far left. He's actually been in some movies recently. So let's first talk about Arrhenius acids and bases. The definition of acids and bases for Arrhenius is that they are entirely based on chemistry and water, and only water. So if it's an organic molecule, it has to be water soluble. And there are many that are, but there are many that are not. So if we look at an example of an Arrhenius acid, a good example is like sulfuric acid. If I take sulfuric acid, put it in a little water, I actually form the hydronium ion and the sulfate. Notice that we often also just write that hydronium as H+ or as a proton. They both mean the same thing. If I look in an Arrhenius base, again, we're going to look at some inorganic bases because they're more common for Arrhenius. If I take sodium hydroxide, throw it in some water, my sodium hydroxide dissociates into both sodium and to the hydroxide ion. And here it is. So the definition is Arrhenius base is a substance that dissociates in water to give hydroxide ions, and that's what sodium hydroxide does. Unfortunately, most organic chemical reactions occur in solvents other than water. Therefore, a different definition of acids and bases was required. Bronsted and Lowry defined it as a Bronsted acid is any compound that donates a proton, and a Bronsted Lowry base is any compound that accepts a proton. Let's look at an example down here. Here I have a carboxylic acid, and on that carboxylic acid I have this H over here shown in red. It is actually a proton. Here I have a methoxide ion. It is lacking a proton, so this is a proton base. It wants a proton. When I put those two together in solution, my carboxylic acid loses a proton, so it's an acid. My methoxide ion gains a proton, so it's base. So here is the molecule after I lost the proton, and here is the methoxide after gaining a proton. Notice that now this has become a base because it wants a proton, and this one has become an acid because it wants to lose a proton. And if I look at the chemical reaction here, notice that it is drawn as an equilibrium reaction, with the equilibrium pointing mostly to the right-hand side or the products. Note that this is a more complete definition, and it also includes all the Arrhenius acids and bases. So I can, if I had a water-based system, that could also be a Bronsted-Lowry acid or a Bronsted-Lowry base. While good for many applications, the Bronsted-Lowry definition of acids and bases is limited to proton transfer reactions. The Lewis definition expands on that, and he talks mostly about the electron pairs and their movement. Electrons and their movement is very common in organic chemical reactions. After all, we're either making bonds or we're breaking bonds, and those are electron movements. So a Lewis acid is a molecule that accepts an electron pair. So Lewis acids are electron deficient and they want more electrons. A Lewis base wants to donate an electron pair because Lewis bases are electron rich and they just want to give them up. So if I look over here at the reaction on the right hand side of the page, you can see that this methoxide ion has extra electrons and is very reactive. So let's see, extra electrons, it's electron rich, that is a Lewis base, and it wants to give them up. This molecule here, this chloromethane, the chlorine is very electronegative, so it's pulling electrons away from the carbon, making it a little bit positive, so it can actually attract extra electrons. So this is a Lewis acid. It wants more electrons. And so I see the movement of electrons here from the oxygen lone pair toward the electropositive carbon, but that would create a new bond, but I have too many bonds now to carbon. I have 5, so I break that chlorine bond. So in this example, I have no protons being transferred. I'm not in water. So I needed a new definition. Okay? All Arrhenius acids are Lewis acids. All Arrhenius bases are Lewis bases. All Bronsted-Lowry acids are Lewis acids, and all Bronsted-Lowry bases are Lewis bases. Let's take a look at the Lewis relationship to Bronsted-Lowry. For example, here I have a molecule that has extra electrons, so this would be a Lewis base. This proton here, it wants electrons, so it's a Lewis acid, but there's a proton being transferred here, so this would also be classified as a Bronsted-Lowry acid-base reaction. If this were done in water, it would also be classified as a Arrhenius acid-base reaction. Let's now take a more in-depth look at the Bronsted-Lowry theory of acids and bases. It turns out there are many organic molecules where a proton can be transferred. For example, if I have a carboxylic acid, it has a proton on it that I could lose. If I have an amine, it has a lone pair of electrons that can act as a base, so I can actually do a Bronsted-Lowry acid-base reaction in organic chemistry. This diagram shows sort of a cartoon representation of a Bronsted-Lowry acid-base reaction where the acid contains a proton that it wants to lose and the base accepts a proton. So in a Bronsted-Lowry acid-base reaction, molecule A loses a proton and molecule B gains a proton, as seen here in this products here. Notice in this case, I actually have a positive charge now on my base. That is not always the case. Let's now look at some examples of Bronsted Lowry acid-base reactions, and let's start off by looking at some inorganic and some traditional acid-base reactions. If I take hydrochloric acid and I mix it with some sodium hydroxide, HCl, hydrochloric acid, is a very strong acid. Sodium hydroxide is a very strong base. So HCl wants to give up its proton. Sodium hydroxide wants to accept it. And in solution, I look at the products, I find that is true. My OH has now been attached to my hydrogen, and I form the sodium chloride salt. Notice that the equilibrium is pushing toward the products here. And so this is a very favorable reaction. And it's a very violent reaction, mixing a strong acid with a strong base. In this second example, I again take inorganic compound, sulfuric acid, which is a very strong acid, and I react that with NH3, which is a mild base, a weak base. Again, I transfer that red proton over to the nitrogen, and in this case, notice that my product here is actually positively charged. So I formed a new bond between my nitrogen and my hydrogen. If I expand that now to organic compounds, if I were to take a strong acid like hydrochloric acid again, and I were to react it with an alkene, this alkene is actually a proton acceptor. These electrons here in the middle of the molecule, these pi electrons, are very reactive, so I can actually add a proton to one of these two carbons here. Notice my product here has a new bond. I've accepted the proton at this N carbon here. We'll talk a lot about this type of reaction when we get to the alkene chapter. And finally, down here, our third example, I take nitric acid, also a very strong acid, and I react it with this proton acceptor molecule, again, having pi electrons here that accepts a proton, because these are negative, there's extra electrons there. I also have a lone pair of electrons on my nitrogen. It wants to accept some positively charged atom, and so I form a new bond between the nitrogen and my hydrogen. Each one of these cases, I've seen that I've transferred a proton from one molecule to another. Remember that a proton is just a hydrogen without an electron. It's just a proton in the nucleus. When we talk about proton transfer reactions, acid-base reactions, we often talk about the conjugate acid. This is the acid that results when a base accepts a proton, so it's one of the products. The conjugate base results when an acid donates its proton. It is actually one of the products also. So if I look at the cartoon representation of a Bronsted Lowry acid-base chemical reaction, this red dot over here with H on it is my acid. We sometimes refer to this as the parent acid. The yellow-orange B here is my parent base. They react to form A without the proton and B with the proton. Now this A is actually basic because it no longer has a proton on it. It wants to react and go in the reverse direction, so we call this the conjugate base. This molecule now has a proton on it, and it wants to give it up, so this is acidic now. So it's the conjugate acid. We usually talk about these always in pairs. I have a parent acid and its conjugate base. I have a parent base and its conjugate acid. Notice the only thing changing here is actually which molecule the proton is on. Okay? And the word conjugate always refers to the products in this case. And we usually draw those on the right-hand side of the molecular reaction equation. Again, notice that this reaction is reversible, so it's in equilibrium. If we look at some of these examples over here on the right, if I have sulfuric acid, it wants to give up a proton. In this case, water can actually act as a base. It has lone pairs of electrons here that can actually accept a proton. So during the reaction, if I mix those together, I form the hydronium ion. In this case, that's the conjugate acid. This is acidic. Okay. The conjugate base now has extra electrons on it that want a proton, so my sulfate anion is actually my conjugate base. Parent acid and its conjugate base. Parent base and its conjugate acid. And the second reaction here, water is now acts as an acid because it has hydrogens on it, and ammonia here acts as the base. So its lone pair of electrons can actually attract one of these hydrogens here and form NH4+, and my water loses a hydrogen to form the hydroxide anion. So in this case, parent acid, its conjugate base. Parent base, its conjugate acid. Notice that these are all in water, so these would also be considered Lewis acids and base reactions. If we look at this second reaction down here, this is an actually more organic-like molecule. This is ethanol. It is an alcohol and it contains a hydrogen on it, which is very, very weakly acidic. The NH2- is very basic, so when they are reacted together in a reaction vessel, my alcohol loses a proton and my NH2- gains one. So ethanol is my parent acid. Its conjugate base is the oxide anion. Here my NH2- is my base, and its conjugate acid, it now has the hydrogen that wants to be lost, is H3N. If we look at a chemical reaction of two organic molecules, here I have a carboxylic acid and a methoxide anion. The carboxylic acid has a proton. Just the word carboxylic acid should tell me it's an acid, okay? And so after I mix these two in a reaction vessel, they react to actually form the conjugate base and its conjugate acid. Okay? Notice if I look down here at all these equilibrium constants, some of them point in the direction of the products, and some point in the direction of the reactants. So this tells us which direction is most stable for the reactants to occur. In the second equation here, the largest arrow is pointing toward the product. So if I were to take a snapshot of this equilibrium, I'd have more reactants than I do products. So equilibriums favors one direction or the other. Let's take a closer look at some reversible reactions. So most acid-base reactions are reversible. A strong acid, the products are favored in the equilibrium. So if I look at this reaction down here, and I know it's inorganic, I take hydrochloric acid, react it with water, I form the hydronium ion and the chloride ion. So this reaction is very favorable, and in fact it's exothermic, so it gets very hot. A weak acid, the reactants are often favored. So if I look down here at the reaction of acetic acid, which is just vinegar, and water, I notice that the reaction arrows here actually point in the reactants direction. So if I were again take a snapshot of the equilibrium in time, I'd find out that there are more reactants than there are products. But I can still find that there are some products. There are some anions of the acetate anion, and there are some hydronium cations in solution. We can actually quantify those equilibrium by determining the Ka. So let's take a look at a generic equation here where I take any generic acid, I throw it in water, I form the hydronium cation, and I form the acid anion. So if I look here, this would be the parent acid. Its conjugate base would just be A. In this case, my parent base would be water, and its conjugate acid would be H3O+. Whenever we determine the equilibrium constant for a chemical reaction, we want to take a snapshot and see how many products we have divided by how many reactants we have. And here's that equation here. The equilibrium constant for that reaction here is the concentration of my hydronium ions and my acid ions, those are two of my products, divided by the concentration of my reactants, which is water, and my original parent acid. Okay, that tells me the concentrations relative of products relative to reactants at any given time at equilibrium. If I rearrange those a little bit, I find out that my acid dissociation constant, K sub A, is equal to the amount of my hydronium cation times my amount of my acid anion divided by my original acid concentration. We call that the acid dissociation constant. If we measure the concentration of our products versus reactants, we find out that we get a numerical value for those at equilibrium. If I look at some examples here, if I look at hydrochloric acid, HCl, and I measure those concentrations, I come up with a value of 1.6 times 10 to the minus 2 for my Ka, meaning this is a very, very strong acid, because the larger the K sub A, the stronger the acid. Even though this seems like a very small number, it is actually larger compared to others. For example, if I look at the equilibrium constant for acetic acid, which is a weak acid, it has a K sub A of 1.6 times 10 to the minus 5. It's even smaller. If I look at methanol, it has a K sub A of 3.2 times 10 to the minus 16. It is very, very small. And if I look at methane, a true, just simple organic compound with carbons and hydrogens, it has a K sub A of 1.0 times 10 to the minus 50, an extremely small molecule. So the larger the Ka indicates a strong acid. So in this case, hydrochloric acid is considered a strong acid, acetic acid weak, methanol very, very weak acid, and methane very, 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 very weak acid. Okay. Unfortunately, these values are sort of cumbersome because they're such a broad range and they're so small to start with. So we often take the negative log of the K sub A and we get something called the pKa. And acid strength is now compared by pKa's rather than Ka's because it makes the numbers a little more manageable. So if I take the negative log of the Ka, what I find out is that hydrochloric acid has a pKa of minus 1.79, acetic acid 4.8, methanol 15.5, and methane of 50. Notice in this case, my largest number now here is my weakest acid, and my smallest or negative number is actually my strongest acid. That's because I'm taking the negative log of these values. Okay, and that reverses the order based on whether it's large or small. So smaller pKa's indicate stronger acids. Larger pKa's indicate stronger bases or very, very, very weak acids. Understanding the relative strength of acids in organic chemistry is very important. We do not do any math here, so we don't do any calculating of pKa's or Ka's or anything like that, but we do need to know the relative strength of acids, and we can just look at the pKa's for that. Small numbers mean acidic, large numbers mean basic or very, very weak acids. Let's look at some examples. Okay, so if I look at just the pKa, remembering the smaller the pKa, the more acidic. So if I look at very strong acids, they are less than 1 and sometimes they're actually negative, like in HCl or sulfuric acid. Moderately strong acids are ones that are pKa values of 1 to 3. Weak acids have a pKa value of 3 to 5, which is for acetic acid and formic acid. Very, very weak acids have pKa's between 5 and 15, or approximately. We consider alcohols as being very weak acids. And extremely weak acids are molecules that have pKa's greater or much greater than 15. Example, methylamine and ammonia. In fact, these are bases. So let's take another quick look over here. If I have acetic acid or formic acid, their pKa's are approximately 4.76 to 3.75. You should be able to look at that pK and say, that's probably a weak acid. Looking at the molecular structure, I can recognize that there's a hydrogen out here and a hydrogen out here that is a little bit acidic. So carboxylic acids are the most common organic acids. Alcohols are actually very weak acids. They have pKa's in the 15 range here. You can see methyl alcohol has a pKa of 15.5 and ethyl alcohol has a pKa of 15.9. That hydrogen out here at the end of the hydroxyl atom is actually a little bit acidic. The same thing over here with ethyl alcohol. If I look at two amines, methylamine and ammonia, both these are actually not acidic at all. In fact, they're basic. The nitrogen here has a lone pair of electron on it that wants to accept a proton, so these are considered bases. What if we were to protonate amines? For example, if I take methylamine and I put it in a very strong acid, I form the conjugate acid now, which is protonated. It now has a pKa of 10.7. It wants to give up that proton, so it's considered a weak acid now. If I were to take ethylamine, put it in some very strong acid, forming the conjugate acid of the amine, it is now acidic, and so it has a pKa of 11, and it is considered a weak acid. And we play these games in organic chemistry all the time. Okay? I can also protonate alcohols and make them very strong acids, and I can also protonate carboxylic acids and make them even stronger acids. So if I take methanol and put it in, combine it with a strong acid, I form the conjugate acid now of the alcohol, and it has a pKa value of minus 2.5. It's just as acidic as HCl just about. If I take ethyl alcohol and protonate it, I now have a molecule that has a pKa of minus 2.4, very strong acid. If I take a carboxylic acid and protonate it, I now have a molecule that has a pKa of minus 6.1. So I've actually synthesized very strong organic molecules or acids. An alcohol and a carboxylic acid can actually act as an acid or base. So in this first example over here, I have methanol, which is acting as an acid. If I put it in a very strong base, this molecule wants a proton, and the only one available is the one that's very weakly acidic, is the hydrogen, that proton on the CH3O. So I actually form water now, and I form the methoxide anion. So this is my parent acid. This methoxide ion would be my conjugate base. The hydroxide anion is my base, parent, and the water would now be my conjugate acid. It turns out that water can also, or methanol, can also be considered a base. It has lone pairs of electrons on it that are mildly reactive. So in this reaction down here, my alcohol reacts as a base. It wants a proton, so if I have it in an acidic solution, it can pull off that proton. and form this new cationic species. So if I go back over here to the left-hand side, this is my parent base. This new protonated form is my conjugate acid. In this case, I started off, the hydronium ion was my parent acid. After losing a proton, water now is my conjugate base. Notice that the arrows always point from the proton acceptor, or the electrons, to the proton donor. So in this case, my methanol is a base. It is my electrons here that form a new bond with the hydrogen, which makes me break that one here. So I'm always moving my electrons with these arrows from the electrons to something else, in this case to the hydrogen atom. So in the first reaction at the top here, my alcohol was protonated. And in my second reaction, the alcohol was deprotonated. A carboxylic acid can also behave as an acid and base. Same concept here. Here I have a carboxylic acid, but if I have it in a very strong basic solution, this hydroxide ion, its electrons can actually react with that hydrogen, breaking that bond. So here's my parent acid. After the reaction, I form the carboxylate anion, which would be my conjugate base. My hydroxide anion is my parent base. After the reaction, it now forms my conjugate acid. Notice in this first reaction, the equilibrium points toward products. So I'm actually deprotonating the carboxylic acid in this case, and the carboxylic acid acts as an acid. If I instead were to put that carboxylic acid in a very strong acidic solution, the lone pair of electrons on this oxygen here can actually react with that strong acid, the hydronium ion, to form a new bond. So I'm protonating my carboxylic acid, and I'm deprotonating my water molecule here. So here's my parent base. Here would be its conjugate acid. Here's my parent acid. This would be my conjugate base in this reaction. Carboxylic acid behaving both as an acid and a base, because it not only has a hydrogen which it can give up, it's got lone pairs of electrons which can be protonated. Amines can also behave as acids and bases. In this first reaction, my amine is actually behaving as an acid, which is not the normal situation. But if I put it in a very strong base like sodium hydroxide, I can actually pull one of these hydrogens off my amine to form this anionic species here. And my base here will now be protonated. So here's my parent acid. Here's my conjugate base. Here's my parent base. Here's my conjugate acid. Notice I formed a new bond here. So in this reaction, I'm deprotonating the amine. In normal organic chemical reactions, amines behave as bases. They're set up here to have a lone pair of electrons which can actually react with hydrogen to form a new bond. So I've formed a cationic species. Because nitrogen is a little more electronegative than the carbon here, it happens to be a favorable reaction. So in this case, this is my parent base. Here's my conjugate acid. Here is my parent acid. Here is my conjugate base. Let's look at the equilibrium for both of these reactions here. Notice in the top one, I actually favor the reactant. That's because the base is actually more stable if it just has the hydrogen attached to it. In the second reaction, notice that my products are favored. So if I take amines and put it in acidic solutions, they want to be protonated. And that is a stable configuration for amines, being a cationic species. Okay. Let's now just sort of review some of these principles here. When I have a very low pKa, I have a strong acid. So when we think of normal acid-base reactions in water, we think of the hydronium ion or cation. That's a very strong acid, HCl, H2SO4. In organic chemistry, to make a strong acid, I typically have to protonate something. So if I protonate an alcohol, I form a very strong acid. If I protonate a carboxylic acid, I form a very strong acid. If I look at just carboxylic acids that are sort of normal, they have a pKa of around 5. That should tell me that this molecule is actually sort of a weak acid. And again, that's why we call it a carboxylic acid, because it actually is weakly acidic. If I look at molecules in organic chemistry that are sort of moderate or weakly moderate acids, something around 10, like a protonated amine, would be a moderate acid. More commonly, though, we actually think of alcohols as being very weak acids. So I look at alcohols or water. They are considered to have a weak acid.